Do not cross planar graphs. Euler theorem for planar graphs. Let us assume that a farming community has 3 houses and 3 wells. The families living in the 3 houses cannot stand each other, so they prefer not to meet when they walk to the wells. Can we build roads from each of the houses to each of the wells so that there will be no 2 roads among the needed 9 roads that intersect? Figure 12.1 shows a credible but failed attempt to build such roads. Now you could think that maybe another attempt will succeed, or after many unsuccessful tries, you may think that arranging the houses and the wells differently might help. Both of these hopes are false, however. The 3 houses, 3 wells problem cannot be solved. In this section, we will develop a theory to prove this claim. It is clear that we are dealing with the graphs from a new aspect here. That is, we want to draw them so that their agencies do not intersect. This property is central to our chapter. Definition 12.1. Let G be a graph that can be drawn on a plane surface so that no 2 of its agencies intersect. Then G is called a planar graph. Let G be a planar graph and draw G on a plane with no intersecting agencies. Then the agencies of G partition the plane into regions. We will call these regions the faces of G. See figure 12.2 for an example. The number of faces of a planar graph is just as important a parameter of that graph as the number of agencies or vertices. The following theorem shows that the close connection between these 3 parameters. Theorem 12.2, Euler's theorem on planar graphs. Let G be a connected planar graph with V vertices, E agencies, and F faces, then V plus F is equals to E plus 2. We prove the statement by induction on E, the number of agencies of G. If E is equals to 1, then G is either the tree of 1H, and then V is equals to 2, F is equals to 1, and the statement is true, or G is the one vertex graph with a loop, and then V is equals to 1, F is equals to 2, and the statement is true again. Now let us assume that we know the statement for all graphs with E minus 1 agencies, and let G have E agencies. We distinguish 2 cases. If we could omit an HE from G so that the new graph G' is still connected, then E is in a cycle in G, and therefore there are 2 different faces on the 2 sides of E in G. Then G' has E minus 1 agencies, V vertices, and F minus 1 faces, as the omission of E turned the 2 faces on the 2 sides of E into 1. Therefore, V plus F minus 1 is equals to E minus 1 plus 2, so V plus F is equals to E plus 2. If there's no E with the mentioned property, then G is a cycle-free connected graph, that is, a tree. Then we know that V is equals to E plus 1. On the other hand, F is equals to 1, so the claim is again true. Now we are in a position to settle the problem of 3 houses and 3 wells. Indeed, that problem is equivalent to the problem of drawing K33 on a plane surface without crossings. Example 12.3. The graph K33 is not planar, therefore there is no solution for the 3 houses, 3 wells problem. Solution. Let us suppose that K33 is planar. As it has 9 agencies and 6 vertices, it follows from theorem 12.2 that it must have 5 faces. However, K33 is a complete bipartite graph, so all its faces must be quadrilaterals. 5 quadrilaterals need 20 agencies, but in a planar graph, each edge is contained in 2 faces. Therefore, our graph would need 10 distinct agencies, but it has only 9. Note that in particular this means that it does not matter where the houses and the wells are located with respect to each other. No arrangement will work. As K33 is a subgraph of K6, it follows from example 12.3 that K6 is not planar. On the other hand, K3, the triangle, is obviously planar, and so is K4, as the reader can see by drawing a square and its two diagonals, then replacing one diagonal by an outer edge. It is less obvious to decide whether K5 is planar. Example 12.4. The graph K5 is not planar. Solution. Again, let us suppose that K5 is planar. As it has 5 vertices and 10 edges, it follows from Theorem 12.2 that it must have 7 faces. As K5 is a complete graph, all its faces must be triangles. 7 triangles, however, would need 21 edges, which is impossible as each of the 10 edges of K5 are used in exactly 2 faces. It is not by accident that we choose K5 and K3 for our examples of graphs that are not planar. Certainly, if G contains K5 or K3 as subgraph, then G cannot be planar as we cannot even draw a particular subgraph, the K5 subgraph or the K3 subgraph of G, without crossings. The interesting fact is, however, that in some sense, these two graphs are the only ones that can cause a graph to be not planar. Let us make this statement more precise. It is clear that if H is a graph that is not planar, and we remove a vertex V of degree 2 from H, contracting the edges A, B, and V, B into a single edge A, B, the obtained graph is still not planar. Similarly, if we split an edge CD of H into 2 edges by inserting a vertex F into the middle of CD, and thus replace the edge CD by the edges CF and FD, we again get a non-planar graph. If a graph T can be obtained from H by repeated applications of these two operations, then we say that H and T are edge equivalent. Then the following theorem that we will not prove characterizes planar graphs. Theorem 12.5, Kuratowski's theorem. A graph is not planar if and only if it contains a subgraph that is edge equivalent to K5 or K33.